Okay, let's get started. All right, so we're. Hang on. Let me just try and fix this echo. Quit. Okay. So we're talking about trying to pull together all these tools and interpretations we've developed so far. So we started off talking about systems, then we looked at the Fourier transform as a way of understanding signals and systems in terms of their frequency content, in terms of them being built up out of individual sinusoids, which could each be modified by the system, but they would still remain the same frequency. And then we looked at the Z transform as a way of, it's basically the same expression as the Fourier transform, but just generalizing. So rather than summing x of n e to the minus j omega n, we're summing x of n z to the minus n. So if z is e to the j omega, then we get the same result. But by thinking about it as thinking about the process of taking a transform as a polynomial in z, then we can think about it as the surface on the z plane. The Fourier transform, the part we're interested in, is this unit circle, but then the behavior of what's going to happen on that unit circle is determined by the roots. If we happen to have a closed form of a rational polynomial, the roots of that rational polynomial, the poles and zeros, which are, maxima and minima of this surface, and then it's where the Fourier transform, the unit circle, slices that surface, gives us the Fourier transform. So now, in topic 5, we've just returned to the idea of the Fourier transform as this sort of way of, as this window onto our systems by talking about the frequency response. And then we're going to link that to the Z transform to sort of try and close the loop, as it were. So the idea of the frequency response is that if we take, modulo some issues about transients, but generally speaking, if we take the Fourier transform of the impulse response of a system, we get this function here. So this is the our moving average filter, which we can think of as a simple impulse response of m equal valued points, right? Just like this sort of blurring with a rectangular blur. And then we can look at the magnitude and phase of that impulse response. And it has this, turns out to be this periodic sinc function where it has a peak around omega equals 0, and then it goes down, diminishes, gets smaller for larger values of omega up to pi, and then because of the 2 pi periodicity here and the symmetry, has to come up again to have a peak at 2 pi and minus 2 pi. But it's basically got this central lobe and then some small stuff down here. That's the magnitude response. The phase response is basically this linear phase, which corresponds to a delay, right? The Fourier transform of pure delay is e to the minus j omega n0 for a delay of n0 samples. So this would be a delay, but then every time this magnitude does a sign flip, that involves a pi jump. So it looks jagged, but these kinds of phase responses with a linear part with some jumps in is something you'll see a lot, and it's a characteristic of a pure delay or a pure time shift. So that's saying, well, for any frequency we put into the system, this should tell us the magnitude that comes out and the phase of the sinusoid that comes out. And so if we have an input which is, say, 2 complex sinusoids like this, then we can look at the frequencies of these sinusoids. So omega 0 and omega 1 are some constant frequencies, radians per sample, of these 2 sinusoids. We can look up here to find where they are, and then we can just read off the magnitudes and the phase shifts that those sinusoids will experience. So let's say that omega 0 is 0.1 pi, omega 1 is 0.5 pi. This means it'll complete a 2 pi cycle in n equal 20, or in 20 samples. So it's a sinusoid with a period of 20 samples. This one will complete it in 4 samples, so it's a sinusoid going 0, 1, 0, minus 1, etc. But now if we look at this, well, here's 0.1 pi on this. This is pi, this is 2 pi. 0.1 pi. The gain is close to 1. The phase shift is a little bit negative. So the gain is maybe 0.8 with some phase. And then for this at 0.5 pi, which is here, the gain is much smaller. It's maybe 0.2, although originally it was a negative 0.2, but the magnitude will be 0.2, and then some phase in there. And so what the frequency response idea is telling us is that, well, if this is the input, if this describes the magnitude and phase response of the system, then the output will just be these two sinusoids with their magnitudes and phases modified. And so we don't have to actually do the convolution. We can just sort of write them down like this. And so here's the actual result. The blue line is the input, and so you see it's got this. I haven't stemmed these; I've just connected them. But you can see that the rapid variations here are the 0.5 pi radians per sample sinusoids, because it just goes 1, 0, minus 1, 0, 1, 0, minus 1. And then that's superimposed on this slower sinusoid, which is a 0.1 pi sinusoid, which you can see is completing one cycle in about 20 samples here, 20 samples. Right, so the blue line is what you'd expect to see if you summed up unit amplitude, cosine phase sinusoids of these two functions. I've written them as complex here, but if we just took the real part, which would be the cosine of those two phase functions, then this is what we get. So that's the blue function. Then the red function is what we get out of the 5-point moving average, where remember this is just taking the average of the most recent 5 points, which is this thing here. And you can sort of see, you can still see this period 20 sinusoid in there. And you can still see something else on top, which is sort of, more rapidly fluctuating. But the relative amplitudes have changed. So now the rapidly fluctuating part is much smaller in amplitude than the slower moving part. And that's what we're saying here. We're saying we expect the slow moving part itself may be a little bit smaller. It's kind of hard to see, but you could believe that maybe it's been reduced by 0.8. But the rapidly moving part is much smaller, which is what we expect here. So in the MATLAB diary for last time, actually, here, this one, illustrating how the effect of a given system is predicted by frequency response. What we do here is we just sort of go through, we build up these signals, we calculate the actual convolution here and plot it. And then we compare it to just actually evaluating H1 and H2 at those two values. So we take we calculate the DFT of the impulse response to this system. Sorry, that's not very easy to read. Work out H1 and H2 at the two frequencies, 0.1 and 0.5 pi radians per sample, and then just calculate explicitly the sinusoids at the right frequencies scaled by these gains and modified by their phases, and plot them. And that's what there's something slightly messed up in this picture, but that's the general idea here, that here are the slow and the fast sinusoids, here are their original sum, and then the green is the output of the filter, which is what we just saw on the slide. Here is supposed to be the scaled and phase-shifted things. There's something that's not meant to be a kink here. I just plotted it wrong when I was doing this quickly before class. And here's the superposition of the output, this green line here, and the sum of these two sinusoids, which are the infinite duration sinusoids scaled by the appropriate gains. And we see that, they line up pretty well, except, of course, for negative time, where the actual system has 0 input and 0 output. But the infinite duration sinusoids, of course, carry on. And then around 0, there's this, they're both non-zero, but there's some difference. And that's the transient response again. That's the fact that, yes, they're not going to be the same because there's some region where the sinusoids turn on where they're different. But because the impulse response here is only 5 points long, And we said the transient difference was was dictated by the tail of the impulse response after n points. Once we've gone more than 5 points in, they're actually identical, right? Because the transient response has finite duration in this case. So it all works out, and it's kind of, it's a very literal demonstration of the idea that, yes, if you have a system with sinusoids, a finite number of sinusoids as input, then the output will be constructed from a finite number of the same finite set of sinusoids, just with their phases and magnitudes scaled. Okay. Any questions about that? Okay. So now we can stick these things together more rigorously. And so this is the idea of the transfer function. Now, all these concepts, they kind of blur together, so sometimes I get the names confused because they're not that distinct. But the idea of the transfer function is now how we can interpret the z-transform in terms of something like a frequency response. So here are some things that we've seen before. The linear constant coefficient difference equation. We can express a system, a setup, with this sort of most general form of the time domain relation between them. The sum of some finite range of values of y and some chunk of y with some coefficients. Sum of those is equal to the same kind of thing for x. Right? So here it's just saying there are two sequences x and y. I can calculate this, which is another sequence based on y, but based on some window of values of y. I can calculate this, which is another sequence based on some window of values of x, and those two sequences will be the same for all n. Of course, I can rearrange this to make it yn as a function of x of n and n minus k, and y of n minus k for previous values. I can rearrange this into a causal expression, but the math doesn't really have a sense of time evolving. It assumes that time is already all there. If we have this expression, this is actually something we can take the z-transform of the whole expression. I mean, the z-transform is just a way of transforming into the z-domain. It's linear over the sum, so we can take the z-transform of each one of these individual terms. And we know what the z-transform of this thing is. The z-transform of a delayed version of y is just z to the minus k times y of z. And then we scale it by dk, so we just get a scaling function here. Same thing on the right. So we just get the z-transform of this expression. You can think of this, like I said, as a sequence derived from x. And so this is the z-transform of that sequence. But the LCCDE is saying these two sequences are the same, so the two z expressions are the same. And then we can rearrange. We can just take y of z as a common factor out of here, do the same thing over here, and then divide through by the common factor of y of z to get this expression. Y of z is equal to this pair of polynomials, a rational polynomial in z, whose coefficients are given by the LCCDE coefficients, times x of z. And we can call this whole thing h of z. And so now we have our z-transform expression, which is equivalent to this LCCDE expression. So the LCCDE written in the z-domain is like this. Y of z is h of z times x of z, where h of z is this rational polynomial in z with coefficients coming from the LCCDE. Now, of course, and we call this h of z the transfer function. This expression looks familiar because, of course, when we were doing the z-transform, it was the whole point was that it was inheriting this property of the Fourier transform that convolution in the time domain becomes multiplication in the transform domain. So that if we have y of n is x of n convolved with some impulse response h of n, then we have y of z equals h of z, x of z. So we have these two expressions, both of which are y of z equals h of z times x of z, but the h of z is coming from different places. On the previous slide, h of z was this rational polynomial coming from the LCCDE coefficients. And in this slide, it's the Fourier transform of the impulse response, sum of h of n z to the minus n. Okay? Well, if they're the same input and output in the same system, meaning the same system, then these things have to be the same, right? There's only one relationship between y of z and x of z that in general will work for all inputs. So these things must be the same. And so let's just think about that. Well, let's think about a simple case like an LCCDE where the system is just a set of, it's like a set of delays and gains. So it's a finite impulse response filter where we can write down the impulse response as a set of a finite length set of values, which is the same as like this. If you put an impulse in, you get this output h0, h1 through to hm minus 1. So you could build that by having a system with a delay, set of delays, and then these things coming off as gains off various stages of that delay, so that each feeds the output in turn as the impulse worked its way down the delay line. So that would mean it would be the same as having on an LCCDE. It's the same as having these p of k's be the individual h of n terms, because that's going to work out. And then also having just a single term on the left-hand side. So the d of k's are 0 for k greater than 0. So we only have one y of n term involved. So then the difference, the LCCDE becomes this. This is the d0 term. Here are the pk terms, which are just hk. And so we end up with, the LCCDE becomes the convolution equation. And so these things are the same. Here we're saying that, well, the pk's are the h of n's, and this sum of dk z to the minus k, it's only d0 that's non-zero, so this just becomes 1. So these things are equivalent. So in that simple case, we can see that these two things are the same. What's interesting is that, of course, it still works even when we have non-trivial d of k's, meaning feedback, meaning a non-finite impulse response that may go on forever because it's got some feedback going on. So it's actually hard to write it down in this way, but we can still deal with it nicely in this way. So I mean, there's nothing. This was sort of had to come this way, had to work out this way because of the way the Z transform encompassed the Fourier transform, and I don't know, because of the way the systems were built out of Fourier transform. So there's nothing particularly revolutionary, nothing new that we've put in here, but still putting it together in this way is maybe something that we hadn't quite seen before. In particular, the way that the LCCDE more or less goes straight to this rational polynomial in Z, which we've sort of seen as this powerful way for understanding what's going on in the Fourier transform, right? Because once we get this polynomial in Z, we can find its roots, we can figure out then we can understand what the Fourier transform is going to be. So let's do that now. Here's our moving average filter again. And so here it is in terms of an impulse response, that it's if you put an impulse in, then you get 1 on m out for the first m samples and 0 everywhere else. So that means h of z is the Z transform of the impulse response, which is this. A finite geometric sum in just z to the minus 1, actually. Here's our finite geometric sum identity. If it was an infinite sum, if it was a convergent infinite sum, it would be 1 over 1 minus z to the minus 1. Because it's finite, it's 1 minus z to the minus m over 1 minus z to the minus 1. And then here's the 1 over m term. Here's our rational polynomial in z, or z to the minus 1, where are its roots and zeros? Because that's it's poles and zeros. That's what, as we know, that's what sort of is going to be interesting in understanding what the what's going on in the z-domain. Well, this thing, the zeros are going to be at the solution to this, which is z to the m equal to 1, which means the m roots of 1, right? And because they're complex, that means there are, in fact, m of them. And what it is, it's the values of complex m, which when we raise it to the mth power, brings us back to here. And so obviously 1 raised to the mth power is 1, but also e to the j 2 pi on m, you multiply that by itself m times, it comes back here, or in fact e to the j 2 pi on 2 times 2 pi on m. This thing will go 1 times that, 2 times that, 3 times that, 4 times that, 5 times that, comes back here. So the roots are actually e to the j 2 pi r on m for any integer r, because when you raise that to the mth power, it's just multiplying this phase times m, which will be e to the j 2 pi r, which is back at unity. So these are the roots of unity, as you may have come across them. And for z to the m, they're going to be m of them, and they'll be equal spaced around the unit circle here. So those are the zeros. Looks like we have a pole here. If we have a few poles, if we multiply this through, we have a z to the m minus 1 term, so we have m minus 1 poles at 0. But like I say, we're going to ignore those. What that means is we could have shifted the sequence by, by some number of points if it was a sequence, and we could cancel those out just by shift in time. So they're not that interesting. But here we have a z to the minus 1, which is a pole at z equal 1. We actually already had a 0 at z equal 1. What that means is we've got a pole and a 0, which means we've actually got common factors in the numerator and the denominator. So this is not the simplest expression of this. We could divide this z to the minus 1 out of this term. We'd get some polynomial z to the m minus 1. Graphically, we can just work that out straight off. It's just saying, well, these two basically cancel out, so they disappear. So we're left with a system with 4 zeros and no poles, actually. And then, very small, I've tried to draw here what that surface looks like. So here it is, somewhat bigger. I'm just doing the same thing. I'm just using the same code to sort of plot a closed-form solution. Here are 4 zeros on a log scale. They're these like downward-facing poles. On the z-plane, here's the red is the intersection with a unit circle. It's a little hard to see, but you see this part up around z equal 1 is like higher than all these other parts. And so when we actually plot that, when we sort of unwrap that red line, we get this, the magnitude of h of e to the j omega. That's what it means, magnitude of h of z for z equal e to the j omega, which we recognize as the magnitude response of this moving average filter, the thing we calculated a few slides back when we were slicing it at 0.1 pi and 0.5 pi. But now you can understand that this peak in the middle is like the value, the values of this surface around 0, and then these points where it goes to 0 are actually where it's being pinned to 0 by these 4 zeros here, right? So these are actually, this point corresponds to this point corresponds to this, etc. Because it just happens that the zeros are actually on the unit circle, so when we slice on the unit circle, we get these values of 0 magnitude coming through. And so that's the whole cycle from the impulse response to the z transform to the roots to the frequency response. Yeah.
Can you just repeat why that pole at z equal 1 cancels?
Yeah. So why does the pole at z equal 1 cancel? It's because I can actually, if I have, so I have z to the m minus 1 divided by z minus 1, right? That's some other terms in here. So it turns out if I do that division, right, z minus 1, into z to the m minus 1, then if I multiply by z to the m minus 1, I get z to the m minus 1, sorry, z to the m minus z to the m minus 1, right? And then I get, I have to move this down to the end back here, right? I get 0 z to the m minus 1, etc. So these things cancel out. I get a bunch of terms in here. So does anyone know whether I'm losing my nerve here, but I'm going to get this wrong. But it's something like z to the m minus 2 minus z to the m minus 3. No. Yeah. Are they alternate in sign, or are they all plus?
They're all plus.
They're all plus. And then eventually you get the 1 down here. But it turns out that this is actually, it ends, right? So it turns out that I can write z to the m minus 1 as z minus 1 times some other polynomial which doesn't have any real roots. And so it's just saying that, I mean, when you have an expression like this with a bunch of zeros, all that's saying is, well, these roots are the result of a bunch of z minus zeta I terms multiplied together. But in general, the zeta i's will be complex, and so the terms, if you actually worked out the full polynomial, you get complex values. But it turns out that this set of 4 give you real coefficients, and then you can separate it out to this other term here. There's a simpler way, right? I actually know what this expression is. It's just 1, 1, 1. It's the impulse response. That was the whole point, right? That this is the z transform of a 1, then m minus 1 zeros, and a minus 1. But I know that this whole thing works out to be this impulse response here. So that's why that's the solution of the long division. Thank you for helping me, guys. So it's kind of weird, right? Because, like, well, wait, what? You know, we start off with something, because, like, something which has only got, in LCCDE terms, right? Something that's only got, something that's got an impulse response like this should work out to be a LCCDE with no denominator, right? It should just be numerators. And here we had a system with just a finite length impulse response. But when we actually tried to find its z transform, we ended up with something on the denominator just because we used this geometric series identity. We could have just written down the terms, right? It's just one. It's like there are only m minus 1 terms, c to the 0 through m minus 1. We could have just written them down. But then it would have been, we would have ended up with this m minus 1th order polynomial in z, and it wouldn't have been as obvious that the roots were going to be here. So the point about doing this algebra was just like, oh, it's obvious where the zeros are going to be, and then we just, you know, we end up deleting one of them. But it's all math. It all gives us the same results. If we were better at spotting roots of polynomials, we could have just written down the m minus 1th order polynomial and said, well, clearly the zeros have got to be these m minus 1s, m minus 1 of them around here. Okay. Let's do another example, one that's a little less, has less of a twist, just straightforward. So now, we're starting out with an actual system. It's telling us how y of n appears out of x, some x of n minus 1, x of n minus 2, x of n minus 3, so some past values of x, and some past values of y of n minus 1, y of n minus 2, y of n minus 3. In general, we might expect y of n to depend on x of n, but this system has an intrinsic one-sample delay between input to output. So it actually, x of n doesn't even appear at the output until one sample later. But the system has feedback in that it also depends on the previous values of the output. Okay, but now to do this transfer function analysis, we're going to convert this into a z transform. And now the the way to think about it is, well, if we rearrange this to an LCCDE form with all the y's on one side, all the x's on the other side, we take the z transform of that, we end up with these, bunch of powers, coefficients and powers of z times y, coefficients and powers of z times x. Then we divide through the factors of y to give us our h of z. So when we want to take all these y terms on the other side, which means their signs change, so we get y of n minus 1.3 y of n minus 1 plus 1.04 y of n minus 2 minus 0.222 of y of n minus 3 is equal to this expression in x. When we take the z transform, these coefficients become a polynomial. So we divide both sides. We get y of z on h of z, which is x of z being this, right? These are the coefficients from the x terms. These are the coefficients from the y terms. And we just make sure that we got the signs right. So these terms that we had to move on to the left-hand side had their signs flipped. But otherwise, it's just reading off x of n minus 1 becomes the coefficient for z to the minus 1 on the numerator. X of n minus 2 becomes the coefficient of z to the minus 2 on the numerator. Y of n minus 1 becomes the negative of the coefficient for z to the minus 1 in the denominator. This 1, of course, comes from this thing over here. So you see where we get that, how we go from the time domain expression to the z transform, the transfer function. That might be something you'll be doing next week. So now we've got that. We've got our expression, our finite order, rational polynomial in z. So to understand what's going on, we want to know where the poles and zeros are. So we have to factorize this thing, which, whatever. We have to find, if we take out the z to the minus 1 term, then this becomes the second order polynomial in z. So in general, it's going to have two roots. We notice, just to make sure that this whole thing makes sense, this expression has only real coefficients, which means that if we put a real x in, we're only going to get real values of y out. Which means that if we have a second order expression, at the very worst, we're going to get complex conjugate coefficients, complex conjugate roots out here. If we didn't have, we might have just pure real roots when there's no issues at all, which would mean that we didn't have any kind of oscillating output, because we would just have exponential terms in the Fourier transform of the impulse response. But the worst we're going to have, with second order, we can have a pair of conjugate roots, but they're going to be they can be imaginary, but they're going to be conjugate, because otherwise a real input would be able to give us a complex output, which we can see is never going to happen here. There's no way for complex values to appear within this expression if the inputs are all real. So we know this is going to have two roots. They could be independent real roots, or they could be a conjugate pair of roots. And it turns out in this case they are a conjugate pair. We could find them just by using the quadratic equation, for instance, the minus b plus minus square root of b squared minus 4ac on 2a. Whatever. Now, on the denominator, we have a third order polynomial in z. So we're going to have three roots. So again, we can have a conjugate pair, or possibly two independent real roots. And the third one is not going to be able to be part of a conjugate pair because only one of it is an odd number. So this is going to have to be a real root in order to give us a real expression. It doesn't matter. I mean, I'm just, obviously in general we can just use a sledgehammer and figure out the roots of these things, and they'll be whatever they are. But just to sort of save us time, or to check that what you're doing is making sense, we notice that when we have these pure real expressions, we want these things to give us systems that are going to have pure real impulse responses. Okay, well, I picked these to have sort of nice, relatively round numbers for the roots. So we've got these two zeros at this and its conjugate. This is the real root, and this is the conjugate pole pair. So we can plot those on on the z-plane like this. So here are two zeros, and it turns out that these things, this is part of a 3, 4, 5 triangle. So these two zeros are on the unit circle. Again, doesn't happen in real life, but happens in examples in textbooks. And so here are three poles, the one real pole and the conjugate pole pair. This pole zero diagram describes the closed form expression for the z-transform. To understand what sequences that corresponds to, we need to know the region of convergence. Because of the way the expression was written, this is clearly describing a causal system. We're generating y of n by looking at the previous values of x and y, so it's going to be a right-sided system. So we know that the region of convergence is going to be the exterior of some large circle. Obviously it's going to tend to converge for large values of z, because it's going to tend to die away for z to the minus some large number. We know the region of convergence can't include any poles because it doesn't converge on a pole. And so that means, well, the region of convergence is going to be the exterior of the circle that just bounds the largest pole. We could work it through and figure out where we had to use the identity, but that's basically what the answer is always going to be. It's going to be the exterior of the smallest circle that excludes all of the poles. Which includes the unit circle, right? So that's all we had to check, that the unit circle was in that region. So now we do have a system with a valid Fourier transform, and we can do and we can evaluate the Fourier transform by using this z-transform closed form expression. Otherwise, the closed form expression wouldn't be valid for the Fourier transform. And so now that we know that, we can think, well, what's this Fourier transform going to be? Well, it's got a couple of zeros. It's going to be zero, these particular frequencies, right? Because it's sitting right on a zero. But it's also going to, but apart from that, it will have these poles which will try and pull it up in that region, and another pole here which will tend to make it bigger. It's a little bit complicated to think about exactly what it's going to do. But that's the sort of the thinking, that's the reason we're doing this, so we can think about that, and so we can look at the system, and we can immediately get a little bit of a sense of what's going to happen when we put different frequencies into the system. It's kind of annoying that we don't actually get to see this right now. I don't have a plot of the surface for this, but what we're going to do now is go through how we can maybe understand that a little more quantitatively. But I guess the important part is that once we get from the system expression, the description of the system, to this pole zero diagram, we've basically got a much deeper insight into what's going on in the system. We've got the tools and the information to figure out what it's going to do in the frequency domain much more directly. So, so what do we do now? We've got we've said that the DTFT is the z-transform evaluated on the unit circle, h of z for z equal e to the j omega. This idea of slicing the surface. This picture is not the system from the previous slide, right? System from the previous slide pack. So h of z is, in terms of these poles and zeros, it's a rational polynomial in z, which we can factor in terms of the individual zetas and lambdas here. That's how we write it when we're trying to get an expression in z to the minus m, z to the minus k. But if we multiply through, or if we divide through by z to the m and z to the n, then these terms just become simple z minus zeta, z minus lambda. It's just to make it obvious that this is a pole when z equal zeta, this is a pole when z equal lambda. If we substitute z equal e to the j omega, then we get h of e to the j omega is equal to this term out here, p0 divided by d0, z to the minus m minus n, which becomes e to the j omega n minus m. And then the products of these terms, e to the j omega minus zeta, eta j omega minus lambda for each of the zetas and each of the lambdas. It's just substituting in. Now, what we said was interesting about the Fourier transform was to evaluate its magnitude and phase as a function of frequency, because that tells us the gain and the phase shift that would be applied to frequencies, the sinusoids of those frequencies fed into the system. So if we have our h of eta j omega, which is just our z transform with z replaced by z to the minus 1 z replaced by eta j omega, then we can write down this magnitude and phase. The magnitude, well, this is a product, or the product and the ratio of a bunch of terms. So the magnitude is just the product and ratio of each of those individual terms. So it's just, this thing is a pure phase term, has a magnitude of 1, so it disappears. It's just this pure scalar gain here, doesn't vary with omega. And then the product of these individual eta j omega minus zeta terms, the magnitude of that, divided by the product of the eta j omega minus lambda terms, the magnitude of each of those. So that gives us the magnitude response directly from just as a function of the poles and zeros. And then we can also take the phase. In general, it'll be the phase. This is a product of a bunch of terms, so the phase is just add. It'll be the phase of the constant term, which is typically real, so has a phase of 0. The phase of this, which is a pure phase term, is just this, omega n minus m. And then the summing up the phase of each of these eta j omega minus zeta k terms, and then subtracting out the phase of each of these eta j omega minus lambda k terms. Right? That's just how it works when you build up something like this out of a bunch of complex factors. And these are things that we actually, are kind of interesting and useful to us, the actual way that a particular sinusoid will be modified by this system. So it might be helpful to have a quick way to figure out to get approximations or even exact values for some of those, for the magnitude response and phase response for particular values of frequency. So here's our expression again, the constant term or a linear phase term, and then these frequency-dependent terms. And then if we're thinking about the value of h of eta j omega for some particular value of omega, then we can think about this part doesn't depend on omega except for the phase, which is just a linear function of omega. These parts do depend on omega, and what we're saying is that they depend on these values here, which we can think of as vectors on the complex plane. And so it's e to the j omega minus zeta I, which is the vector from zeta I to eta j omega. Like it's minus zeta I plus eta j omega. So it's this vector here. And so what this is really talking about is a set of properties of these vectors from the different routes on the z-plane to some point on the unit circle, which depends on which frequency we're talking about. We can sort of think about these as we move around eta j omega for omega equals 0 to pi. Then there are a bunch of these vectors, and you see they're all going to change in length and in angle. And it's the lengths, those lengths and angles are going to determine the magnitude and phase response of the z transform of the entire system. So I'm calling this the geometric interpretation because now we're going to be able to get the actual values of the frequency response, the magnitude and phase response, by thinking about these vectors in a geometric construction. And in particular, the magnitude of h eta j omega is the product of the lengths of the vectors from the zeros, right? It's the eta j omega, magnitude of eta j omega minus zeta I, that was on the numerator, divided by the product of the lengths of the vectors from the poles, the magnitude of eta j omega minus lambda I, that was on the denominators. So on the previous slide, that's the product of these terms divided by the product of these terms, and then the magnitude of that is just the product of length of these terms divided by the product of length of these terms. Those lengths are literally the lengths of these vectors. Similarly, the phase, which we sometimes write as theta of omega, is the sum of the angles of these vectors here. So the angles are relative to 0, and this is actually a negative angle here, right? Negative pi on 4 or something. This one's plus, 3 pi on something, 8. So it's the sum of the angles from the zeros minus the sum of the angles from the poles. And again, as this frequency changes, these angles change, and so the overall phase of the system is going to change accordingly. So now we can think about how the magnitude and phase of a system is affected by individual roots. So we can think about, like, if we have a single 0 here, we can think about varying omega all the way around the frequency response, the frequency axis, and then think about how these vectors change as omega changes, and then think about the resulting magnitude and phase. And so that's what's going on here. Here is the z-plane. Here is eta j omega for 3 different values of omega, sort of 0.1 pi, 0.3 pi here, and 0.9 pi. So here is the magnitude of these vectors. And so here, this vector here is, this is 1. This is sort of about a little bit more than a half. That's that value here. Here, around here, the 0 happens to be kind of close to the unit circle here. So here at the screen point, it's kind of small. That's this point here. And then as we move over here, then we get far away from the 0. So the length of this magenta line, is this point here. And then if we actually plot it, continuously, we get this blue line here. This is the length of the vector from this particular 0 to eta j omega as a function of omega, plotted like that. Similarly, for the phase response, right, the phase is the angle of this vector. Well, here starts off kind of negative, and then it gets less negative, goes to 0 around here, just over 0.2 pi, becomes positive, goes all the way around to pi here, and then does a flip around here, around 0.8 pi, goes negative, but then it becomes increasingly less negative as we go through. So here's that phase response. Starts off negative, goes through 0, changes most rapidly here. For a given amount that we're walking on the unit circle, the angle of this thing changes fastest when we're closest to here, right? You can sort of see that's going to happen. That's this slope here. Here's where it goes through becomes pi, so suddenly it becomes, this angle here is pi, then this angle here is almost minus pi, so that's the flip here. And then it slowly changes as we're going around the circle. So let me just show you a movie. So this is like, I just did that same thing, but I just, in MATLAB, I rendered every value, or stepped omega over a set of values, and then plotted the phase and the magnitude. Let me just play you the movie. I only done it from 0 to pi on this picture. But you see, it's sort of, as this thing moves around, the vector's getting shorter, so this line's getting shorter. The angle's winding up, so the angle's going up here. Then the vector's getting longer, so it's growing out. And then here's where it does its phase flip, stay within the principal value, etc. And then I sort of didn't plot the second half where this thing becomes larger, and then it joins up, because, of course, when you get back to 0, then it's periodic, this magnitude function. But now you can slide this thing around, and you can see what, for every point on this axis where the magnitude and phase lines up. You can see how that point here of nearest approach is the point where the magnitude is smallest and the phase is changing most rapidly. Now, that's a single 0. If we had a pole, well, if this was a pole instead of a 0, then the magnitude impact of a pole is just 1 over this, and the phase impact of a pole is just the negative of this. Right? So now if we Here's the same thing, but with a pole. And so where before we had a dip when we get close to 0, now we have a peak because it's 1 over that. So here it is. The vector is getting shorter, so the reciprocal of the vector length is getting larger, goes through a maximum there, and then gets small again as this thing gets long, goes out to some minimum when it's over here, when it's furthest away, and then builds back up again. And again, we've got the phase. The phase is actually the same function, but just flipped, right? It's just negated. That's all that's going on there. You see that? So now if we have of course, those were single complex poles and zeros. They didn't have their conjugates there, which meant the overall impulse response would have been complex, not something that we would normally encounter. But we can build up a real system out of, by superimposing these sort of elemental contributions of each of the individual poles and zeros. So now we have a system here. It has 2 poles and 2 zeros. Here's 1 pole and 1 zero. They kind of, in this case, they're kind of close to each other and somewhat close to the unit circle at about the same angle. And then here are their conjugates down here in the negative frequency half. So that's, let's say, here it is, like the zeros both have radius 0.8 and angle 0.3 pi. So 0.3 pi is here, and the radius is 0.8. And then the poles have radius 0.9, but the same phase. So they're just 0.8 and 0.9 at an angle of 0.3 pi here. And then we have the conjugate pairs, plus 0.3 and minus 0.3. So now we've got these 4 colors here, and each one of them contributes one of these pieces to the magnitude response, right? Well, okay. Here's the blue line, which is this line here. It's a 0, so it has a dip here, and then a slow, soft maximum over here that goes down. For the red, I've actually drawn the length of the vector here rather than the magnitude response, because what we're going to end up with is the ratio of these two, right? It's going to be the blue divided by the red times the green divided by the orange. By drawing them that way, it's kind of clear that these things are, most of the time, they're pretty close together. So they're going to have a ratio around 1. Their effects are going to cancel out. Over here, right, the blue is 1.8. The red is 1.9. So we divide them through. We get something a little bit less than 1. Over here, the orange, the same. So for every individual frequency, we take the ratio of the 2 close together lines in pairs and multiply them together. This is just, this is how I've done this particular geometric argument. The thick blue line is the overall magnitude response of this system. And so what happens here is, out here, those are about the same, those are about the same. We multiply them all through, we get a number which is about 1. The only place where they're not all balancing out nicely is right here around this point where we're close to the roots here. Over here, the orange is 1.5, the green is 1.45. Their ratio is about 1. But here, the blue is about 0.2, right? This length here is 0.8. So this length here, this is obviously 1. So this is about 0.2. The red, this is 0.9, so this is 0.1. Suddenly, because this is the 0 line, when we divide these two, they're not, even though they're only 0.1 apart, their absolute value is small. So their ratio becomes close to 2, right? That's what we said. 0.2 divided by 0.1 gives us a ratio of 2 up there. And so we get this peak in the frequency response and the magnitude response. And it's localized around where these roots are. Similarly, for the phase response, we can plot the phase response of these things, the actual overall, because I've drawn them sort of in terms of I've drawn the poles as if they were zeros. So it's the difference of the red and the blue curves plus the difference of the orange and the green curves. And so we get this thing where the phase response is close to 0 the whole time. But there is this kink around here because even though they're close to 0, they're close to each other. They have the largest difference around this critical point here when they get close to the root. And so we see the overall phase response, and again, it comes out. But the point being that we can get the overall behavior of the system by building up from the individual geometrically interpreted impact of these individual terms. And so here is the video for that. I've only drawn the overall response. I haven't drawn the individual vectors on this, the individual components. But you can see that as we get closer here, this is where the ratio is largest. We get the peak in the magnitude response, and then it dies away as we go over to higher frequencies. This is quite an interesting system, right? The system where most frequencies are more or less unaffected. They have a gain about 1, a phase about 0. But for some restricted range of frequencies, suddenly the gain becomes larger. The gain is significantly different from 1. Phase is still around 0, although it's not quite so close to 0 as it was the other frequencies. So, this is now beginning to look like an interesting thing, even though it's only got 2 poles and 2 zeros, and is not a particularly complicated thing to calculate in the time domain. Any questions about that? Yeah?
Does the 1 along your x-axis in those cases, or you had a 1 before, denote the Nyquist rate, like in terms of sampling rate here?
Yeah. So does the 1 denote Nyquist rate? So this is this axis here is omega divided by pi. So it's the radians per second in pi, normalized by pi. So it goes from 0 to 1, which is going from here to here on the unit circle in the z-plane. The reason I'm only plotting it from 0 to 1 is because after that it becomes symmetric and has to do this 2 pi periodicity. But that's the same as this concept of the highest frequency that we can represent without aliasing in the time domain, which was called the Nyquist rate. That if we have a sinusoid that advances by more than pi radians per sample, meaning it does more than half a complete sinusoidal cycle every sample, then it looks like a lower frequency sinusoid. It looks, the points sort of have this aliasing effect where they look like they're sort of changing by some slower. They're equivalent to having them change by a lower step every sample, and so that's, they become aliases. They don't look like the frequencies you want them to be, and they become ambiguous. So that's the limit of what pi radians per sample is the Nyquist limit, the largest step we can take before we start looking like something else. I think, yeah. Here I'm plotting the entire range from 0 to 2 pi, just because it's clear that there's an entire circle here, although I've shaded the bottom half and shaded the second half over here to show that it's the symmetric part. So here's this system. It's got this pole and this 0, and we took the Fourier transform. We have these sharp peaks. How does that correspond to our kind of rubber sheet interpretation? Here are the rubber sheet versions of those. So here, and then also in a log plot, so here are the poles poking up, the zeros poking down. In the log domain, these surfaces add up, right, because they multiply together. The magnitude of the overall system is the magnitude of the poles only system, and the magnitude times the magnitude of the zeros only system. So in log domain, the log magnitudes add up. And so what happens is we have a couple of spikes like this, and then we have a couple of negative going spikes. If they were on top of each other, they would cancel out because they would be the same shape. That would be the same as saying we had the same factors on the numerator and denominators. They would just cancel out in the Z transform. But we've moved them apart slightly, but we've moved the poles, the sticking up parts, a little closer to the unit circle than the zeros. And so the overall effect, this is the actual magnitude of the Z transform, which of course goes unstable once we get to a radius smaller than the poles, but shoots up close to these poles. That gives us these bumps. If we just had those poles alone, without the sort of the balancing effect of these zeros, then we'd expect sort of bigger and broader bumps. Like these bumps would sort of just be nice, big, broad, 10-pole type things. By having these zeros right behind them, the zeros are sort of balancing out the effect of the poles over most of the surface, but not right in the very close vicinity to these sort of counter stretches. And so that's why we're left with this bump. And in fact, we could imagine moving these poles and zeros around to get higher bumps or broader or narrower bumps. And now we're beginning to see why the Z transform is this helpful way, this very nice domain for thinking about how to control the properties of systems that we're building, how to control the frequency domain properties of these systems. That's the real point, that you can think about. These bumps are very intuitive to think about, and then moving them around is kind of a natural thing to do. And then thinking about how that influences the behavior on the unit circle, the Fourier transform, sort of emerges naturally out of that. These bumps are also, they're the same thing as what we just talked about in the geometric interpretation. This surface here is nothing other than the product of those vectors, the product and ratio of those vectors. If we just had the zeros, then it, like we had in here, in this one with just the 4 zeros in it, this surface is just the product of the length of the vectors from the 4 zeros to every point on the z-plane. And then for the red line, it's the product of length of vectors to the points on the unit circle. And so that's what that, this is the log of that thing. If we did it, can I do that? Surf. If I don't do it as a log here, oh man. I think x and no. How did I get this before? All right, sorry. I can't get it. But if we didn't have the log being plotted, then these things would just be like nice little cones going down to 0, which is just the length, how far we are away from this point. But it would be the product of all of those. Let me just get that, because what's going on here? All right, no, forget it. Oh, yes, here it came back. MATLAB scripts, visualizing the Z-transform magnitude surface. That's what it was, okay. There we go. So now you can see that, like, without the log scaling, it's not very easy to see at all, is it? Without the log scaling, it's just these nice little, these 4 little linear cones. But when you actually, locally to each one, it's basically the magnitude of the length of the distance from that point down here. but then when we multiply them all together, which is what we're doing, they take on this higher order sort of polynomial shape. So they actually become this kind of fairly steep cone, but they're coming locally from these 5 little linear cones. Any questions about that? Okay, so basically, what was all this about? The point is to, by thinking about the way, as you know, I'm very interested in intuition, and this seems like a very powerful way of understanding what the Fourier transform, what the frequency response is going to do, based on the properties of these simple, easy to visualize properties of the system response, of the transfer function, the Z transform. So here is boiled down to a few specific rules. If we have roots near the unit circle, either poles or zeros, that means that the vector between the unit circle and the root is going to change most rapidly in those particular frequencies, the points on the unit circle that correspond to those frequencies. So we're going to get rapid changes in magnitude and phase. If we have zeros, we're going to see a minima in the magnitude, because that's going to be the shortest possible vector. If we have a pole, then it's going to be the reciprocal of that, so it's going to be 1 over something that's getting quite small, which will be a peak. If we have a zero actually on the unit circle, then that means the magnitude goes to 0, those frequencies. In general, the zeros, which could be anywhere on the z-plane, are not going to be on the unit circle, so they won't lead to zeros in the frequency response. But if they are on the unit circle, then we actually get frequencies whose gain is 0, which means you put that frequency in, you get nothing out. If we had a pole on the unit circle, what that would be trying to say is that the gain would be 1 over 0, which would be infinity. Also, if we had a pole on the unit circle, that would mean that the region of convergence couldn't include the unit circle. It would have to be something outside the unit circle, which would mean we had a system where we couldn't really evaluate the Fourier transform, which would mean the system was non-stable, which is the same as what we'd expect if we had a gain of infinity for some frequency. So actually, poles can't be on the unit circle. They can't even be, and they can't be outside the unit circle for a causal system, because again, then the region of convergence wouldn't involve the unit circle. For these poles for these roots close to the unit circle, we're going to get very rapid changes in the angle relative to these roots for those frequencies, which means we're going to get rapid phase variations. The other thing was this thing that we noticed when we had the pole and zero close to each other. In a way, you can think about their influence on values around the influence of these two roots on values over here is basically the ratio of the two vectors to the ratio, the vector of the zero divided by the vector of the pole. They're about in the same place. The vectors are about the same. So their influence basically cancels out when seen from far away. From far away, they look like they're almost on top of each other, so they're almost a canceling pole pair. So they don't matter. But when we get close to them, of course, suddenly then we can see the difference between them. They're not quite the same place. And so this is this sort of, very kind of back-of-the-envelope way of building a frequency response with features local in frequency. By putting poles and zeros close together, then we can have something which controls what happens in that frequency without influencing the rest of the frequency response too much. That's just something that's relatively easy to think about. There may be other ways, other arrangements of poles and zeros that give us, that have the effect of canceling out or give us whatever response we want over all frequencies. But this is one that's very easy to think about. Okay, so the last thing I want to show you is this tool which was put together by some people from Georgia Tech. There's a link to it on the class website. It's you're kidding me. Okay. Yes. What this thing is it lets us actually directly move the poles and zeros around and see what happens, which is, again, a nice way to see what's going on, to sort of reinforce these things we've been looking at. Okay. Okay. So this is our z-plane, and we can add poles and zeros to this, and then it's going to tell us where these poles and zeros are, and then it's going to update the magnitude response and the phase response. And then this red line here is, we can sample it at particular frequencies to get these things out. So now this is a system with no poles and no zeros, which actually has an impulse response here of delta. It's a identity system. But what I can do now is I can add a couple of zeros. So I click here and then just click here. Then I've built a system with two zeros like this in conjugate pair. It's added two poles at the origin just to make the system have the same number of poles and zeros, but that's just basically a time shift so that the impulse response is all in positive time here. So that's interesting. These two zeros here give me this. It's a system with two zeros, which means it actually has to have a finite impulse response with three values, right? It's just three delays, three alphas, gives me a second order a polynomial in Z, which has two roots here. Here are the zero locations. Here's the impulse response, and here's the magnitude response, which is what we expect, that it goes down closer to zero as we approach these points here. There's a minimum in the magnitude. Then it floats up elsewhere, right? And the phase response, it tends to be negative, but it actually has this rapid increase around the. It's going to have an overall negative trend because there's this sort of thing looks a little bit like a delay. So that would be, if it were just a 1 here, then it would be a linear phase. But it has this, but in the region of these things, these zeros, then the phase increases. It all makes sense in terms of the geometric terms if you think about them. I can add some poles, and I can move them around. So if I have poles over here, right now when I add the poles, I have this feedback. So I have this now no longer limited impulse response. The impulse response carries on indefinitely. It's infinite duration, actually. And then depending on how close they are to the unit circle, that's like how much this peak is going to, how close onto the sort of center of the peak we're going to get. So you see the oscillations become slower and slower to decay, right? They're staying here. And what they're saying is the magnitude response, these peaks in the magnitude response are getting larger and larger and also sharper at the same time, right? So if I move this back, then the peak gain is only like 7, and this thing dies away quite quickly. But as I move these closer to the axis, the peak gain goes up and this amplitude delays. As I move these around, you can see the frequency of that peak changes. As I move them up, this is like 0 frequency, so this is a larger frequency. As I move it closer to omega equals pi, then the peak gets higher up in frequency. As I move it down, peak gets lower in frequency. And you can see here, for this pole relatively close to omega 0 point here, we have this nice slow oscillation. As we move it up, the oscillation becomes faster. And then if I move it close to the 0, I have the same behavior, that if it's just behind the 0, then the sort of 0 dominates here. We get something which is basically flat except for these dips here. If I move it in front of the 0, then we get something which is basically flat, but with these peaks due to the poles. And then I can add more poles and zeros to this thing to sort of have higher order systems and see what happens there. And so you can see what the space of the different magnitude responses you can construct just by out of these poles and zeros. So that's a nice thing to play with. Any questions? Yeah.
What happens if you put a pole
Yes. What happens if you put a pole outside the unit circle? What ought to happen?
It will be unstable.
Yeah. So this thing goes red to indicate that you've got an unstable thing. This impulse response over the first 25 points, it can evaluate it. But you see that it's getting here, it's going to continue diverging, so actually it's not stable. It still plots this because it can still evaluate the Z transform in the unit circle, but it's no longer a valid Fourier transform. Great. All right, see you on Wednesday.